Okay, so this first video is just going to detail some of the helpful Matlab functions that you might encounter when solving linear systems of equations. Go ahead and add this to the template. And if I right-click on my .mlx file, this is a nice shortcut to add the current path. Let's see, did it go? Oh, excuse me, change current folder. There we go. So now my assignment template and the provided Matlab functions for this assignment are available, and we're in the right folder. Now, the first thing I'd like to show is there's this nice command rand. Okay, and what rand does is produces, let me hit F5. Oh, and yes, it's going to run this above example. That's fine. Rand will produce a random number between 0 and 1, uniformly distributed, they say, between 0 and 1. And what I can do is I can introduce any number of random numbers inside of an array or a matrix in general. This will be 3 by 4. That's 3 rows and 4 columns of those random numbers. And I can scale those accordingly if I'd like to, but let me just stick with random numbers. And let's say that this is going to be a random 4 by 4 matrix. Okay, so I can do this. And at the same time, I can introduce a random 4 by 1 vector. And now I might be thinking about solving for x, such that ax is equal to b. And the way I can do that, well, there's a number of ways. So let's add some options. Okay, so option 1 is going to be with RREF. That's reduced row-echelon form. Actually, let me show one middle step here. Okay, and what we're doing here is we're, just like we would by hand, creating an augmented matrix system. Okay, so A, normally I would put my dotted lines between A and B if I were drawing this out by hand, and this is my augmented system. And if I do reduced row echelon form, this is this Gaussian elimination that we would do by hand. So it's going to produce a matrix that is let's see here. On section, okay. So this is going to produce a system, an augmented linear system. Yes, right here. And let me see. Let's get this bigger so we can see it. Okay, and this system has an identity matrix augmented with, well, that happens to be the solution to the system. So what I could say is, let's say that M is this matrix that is the reduced row echelon form of this augmented AB system. X, therefore, is going to be M, and I can select out the entire column. It will be 1, 2, 3, 4, 5th column. So all of the rows but column 5. And if we do that and display X, there it is. Okay, it's the last entry of that augmented matrix. So this is one way of solving the system. There are many other ways to do this in Matlab, and probably the best way is to use the backslash command. And this time, when I have A and B, all I'm going to say is that X is equal to A, and I use the backslash and B. And by the way, a comment on why this backslash, a lot of people are confused about the forward slash and the backward slash. The idea is the following, that if I took this and tried to make it a fraction, I would see that when straightening out this little line, B is in the numerator and A is in the denominator, but A has to be on the left because A is a matrix. In other words, B times A inverse doesn't make any sense. So I think that's the philosophy behind this, is that it should be A in the bottom, B in the top, and A has to be on the left. So that tells us that the left, the backslash, is the right way to form this X. Okay, so that's another way of solving this linear system. Okay, and then there are other things that one would like to know about when considering commands for solving linear systems, or at least for studying linear systems. Okay, so one of them is we could take the condition number of the matrix, and when I do this, I can input a second entry that tells me if I'm taking the 1 norm, the 2 norm, the infinity norm, or the Frobenius norm, and all of those are available in Matlab. Other things I can do, this is more of a curiosity, but I suppose we could call this an option 3. You can construct A inverse and say that x is equal to A inverse times b, but this is typically not used. Slower than the backslash. And really, there's very few times where we actually need to construct the inverse of A analytically or numerically. So the backslash command or RREF are our favorite 2 options. Okay. One other thing that I'd like to show is that we can use Matlab to construct the Lu decomposition. Okay. And let's run that and take a look at L and U as output. Okay. And there they are. L is this, well, let me see, what is going on here? Oh, I see, it's been permuted. Sometimes this happens with a random matrix. There, that one's a little bit of a better demonstration, but it's still been permuted a little bit. But nonetheless, U is this upper triangular matrix and L is this lower triangular matrix. Note here that there's been a permutation, so the one that would normally be in the second entry is up above, and this one has also been permuted. This is for numerical stability, that sometimes a permutation is performed. We didn't really talk about that in lectures, but nonetheless, L is basically a lower triangular matrix with 1s along the diagonal. U is this upper triangular matrix. And what is true is that if I multiply L times U, I'll get that it's equal to A again. Okay. Oh, and I should double check that. So L times U and A. And yes, they're the same thing. In fact, I can even take A minus L times U, and we can look at the numerical errors produced. Okay, and at the 15th decimal, we see 0.1 here and there. So that's 16 decimals of accuracy with MATLAB's LU factorization. Okay, so this is just a few helpful commands for studying and for solving linear systems of equations using MATLAB.